Welcome to week 6 of Classical Mechanics 2. Last week we spent a lot of time talking about Lagrangians and Lagrangian mechanics. This week we're going to consider Lagrangians that involve constraints. How do we optimize something in the presence of a constraint? And we're also going to discuss Noether's theorem, which relates continuous symmetries to conserved quantities. In this video, though, we'll be discussing systems with constraints. So imagine I have this setup here. I've got two particles that are sliding down this frictionless slope. I've got a block of M2 and a block that is M1. The generalized coordinates I'm going to pick are going to be Q1 is the distance that M1 has traveled, and Q2 is the distance that Q2 has traveled. And the constraint here is that Q1 is equal to Q2 minus L. Here is an equation that's expressing our constraint. We want to understand how do we solve problems like this using the framework of variational calculus. Imagine we have n particles with generalized coordinates qi in d dimensions. We have qi's where I ranges from 1 to n times the number of dimensions. For example, two particles in 2 dimensions. Each of those particles has an x component and a y component. We have a Lagrangian that would be x1, y1 for the first particle, x2, y2 for the second particle, and their derivatives for our q dot terms. We can change this into any set of coordinates we'd like. So particle 1 can have qa and qb, particle 2 can also have a qa and qb, and so on and so forth. These coordinates are called natural coordinates if the transformation between my r's, so my Cartesian coordinates, and my q's, the generalized coordinates, does not depend on time. And this is an argument by Maxwell, is that the number of degrees of freedom in the system is the number of particles times the dimension. If I have, again, my two particles in 2D, each one can move in the x and y direction. So that's one particle that moves in the x and y direction. So that's the number of dimensions. And then I have two of those. So that's the number of particles. And what Maxwell said is that the number of degrees of freedom minus the number of constraints is the number of independent equations needed to solve the dynamics of this system. A system is called holonomic if it has the same number of degrees of freedom as it has generalized coordinates. If we want to solve this using the framework of Lagrangian mechanics, let's have a look at this constraint. What we want to do is minimize some functional f of y of x, y prime of x, and x, subject to some constraint, let's say f of y of x, y prime of x, and x is equal to 0. Here we've phrased the constraint itself also as a functional. For our original problem, we define our action as the integral from some position x1 to some position x2 of f dx. Normally what we would do is we'd vary the path y of x and solve delta s is equal to 0. So that's how we approach problems like this in general. Now we'd like to add in a constraint. So how do we vary y without also varying our constraint functional? We want to minimize y while maintaining f is equal to 0 at all times. That tells us that this must also satisfy delta f is equal to 0. And delta f is equal to df by dy delta y plus df by dy prime delta y prime. If we follow through what we did last week, we end up with the Euler-Lagrange equation for f saying that df by dy is equal to d by dx df by dy prime. If I am to say that f remains stationary while we're varying y, we must also solve the Euler-Lagrange equation for F at the same time. This tells us that F also satisfies Hamilton's principle, that the path that minimizes variations in F is going to be the one for which F is stationary. Let's define a new functional. So F tilde of y prime, and x is going to be F of y prime, and x, so our original function, plus lambda times little f of y prime, and x. So this is equal to 0, so we're just multiplying some number lambda by something that's equal to 0. F tilde cannot be changing what f here, our original functional, is. And we call lambda a Lagrange multiplier. We know that since delta f is equal to 0, there's a stationary solution for f tilde that both maintains f here, the constraint being equal to 0, and minimizes our original functional f. To solve this, you simultaneously solve the Euler-Lagrange equations for f tilde, and you solve f is equal to 0 for the functions y of x and lambda, which might be a number and might be a function. In physics, our Lagrangian is equal to the kinetic energy minus the potential energy, and that can be subject to some constraint. We would add lambda times f to it. This is our constrained Lagrangian. dl by dr is what we call a generalized force, and this is du by dr, so the force in sort of the r direction, plus lambda df by dr. So this is the force coming from the potential plus this term here, and this is the constraint force. So if we go back to our original system here, we have a constraint that is saying that Q1 is equal to Q2 minus L, but we can rearrange this so that this equals 0. Q2 minus Q1 minus L is equal to 0. And then when we look at this term here, so we're differentiating that constraint with respect to our generalized coordinates, we end up with a constraint force. So in this case, it's going to be the tension in the rope here that is required for these two to slide down together at a constant acceleration.